Yeah, now it has started. Okay. Okay. I had to start it from the phone. Okay. Nonetheless, okay, so I will quickly repeat that part because it was not part of the recording. So we just started now and we're speaking about operating system operations. And we said that overall, the operating system operates in an interrupt-driven manner. So as a software, it's an interrupt-driven software. So it's an event-based software. And there are two types of events that you often have on an operating system. Is one, normal interruptions caused by IOs or any other application, software applications, etc. These interrupts are handled by what we call interrupt service routines. So these are methods or functions that handle the occurrence of an interrupt. So there is one for each type of interrupt. The second type of interruptions that you encounter on an operating system is what we call traps or exceptions. And these normally happen when there's an error, such as writing to a non-existing memory, meaning a pointer without cast, or memory segmentation of some sort, memory fault, or even division by zero, which would be in this case a logical error, and any other type of error. Normally, the operating system will maintain a list of errors and assign the error code to every error. Like in Windows, the handling of the error is manifested by the popping of a dialog box, which tells you what error has happened, or at least gives you the error code. So the practice in terms of operating system design that's recommended here is to ensure that an error occurring on one program does not affect the performance of the other programs. This is the case of a program that will get stuck in an infinite loop. For example, on Windows once more, when you've got your word processor application saying not responding, sometimes you get stuck there and you can't do other things. But that's a problem when it comes to operating system design. Normally, despite a good operating system design practice would be the one that makes sure that whenever there's an error that occurs on one program, it only affects that specific program. Okay, so the alternative would have been to ensure that there is one program that executes at a time, but that's the problem with that. It makes the entire operating system very slow and reduces therefore its processing performance. I think I've sort of recapitulated on that. Now, 1.5.1, dual mode and multi-mode operation. So when it comes to operations of the operating system, it can be classified as dual mode or multi-mode. In order to ensure the proper execution of the operating system, we must be able to distinguish between the exception of operating system code and the user-defined code. That's very important. What does it mean? So when the operating system is executing, we need to be able, and when I say we, I'm talking about the CPU needs to be able to distinguish between request of execution or of instructions coming from the operating system by means of a code, of course. That's what we call the operating system code. They should be distinguished from request of execution of an instruction coming from the user, meaning these are instructions to the CPU coming from the user application. The approach taken by most computer systems is to provide hardware support that allows us to differentiate among various modes of execution. Okay, so now, if you look at figure 1.10, it shows the transition from user to kernel mode. Okay, we'll discuss it just now, but at the very least, we need to be able to separate. And when I say we, I keep on saying when I say we, it's the CPU. The CPU must be able to distinguish between the user mode and the kernel mode. So the kernel mode, which is also known as the supervisor mode or system mode or privileged mode, as opposed to the user mode, which is mostly initiated from a user application. This can be done, as we just mentioned earlier on, by means of a software, by means of hardware, but it can also be done by means of software in a sense that there can be a single bit called the mode bit. You can think of it as a software flag that is added to the hardware of the computer to indicate the current mode. Whenever we are in kernel mode, that bit mode is set to 0. When we are in user mode, it's set to 1. And if you recall very well, you can boot up a computer in either mode. You could boot, by default, most computers boot on user mode, but you can decide to boot up a computer in kernel mode, especially when you're doing some configurations and so on. That is done on Windows by pressing a specific function key. Now, with the mode bit, we can distinguish between a task that is executed on behalf of the operating system, meaning a system task, and the one that is executed on behalf of the user, which is a user application task. When the computer system is executing on behalf of a user application, the system is in user mode, of course. However, when a user application requests a service from the operating system via what we call a system call, so here the distinction is really between a system call and an instruction call, basically. Now, if a user requests a service from the operating system, from the CPU, but this request is going through the operating system by means of what we call a system call, the system must transition, therefore, from user to kernel mode in order to fulfill the request. Very important. And that's exactly what is shown in figure 1.10. In terms of hierarchy, of course, the kernel mode is closer to hardware than the user mode is. User processes, as I keep on insisting, user processes are mostly driven from user applications. Okay, while kernel processes or instructions are mostly driven from the operating system, and therefore they refer to what we call a system call. Okay, that was important to mention. So the CPU executes two types of instructions at the end of the day. There are system instructions or kernel, in which case the CPU is said to be in kernel mode, and there are user instructions in which case the CPU is said to be in user mode. But it can also transition from one to the other, especially when the user application process requests the service from the operating system. Typical example, you've got a Bluetooth application from which you must start maybe by doing pairing. And when you do pairing, it must go through a Bluetooth API. And because it touches on the Bluetooth modem within the computer, meaning hardware, then there will be a system call through a socket function to the operating system, which will handle the socket part and return the value back to the user application. That socket transaction is handled by what we call a system call, and in that moment, the computer will have switched from user mode to kernel mode. When it gets the feedback from the socket communication or socket request, then it can shift back from kernel mode to user mode to handle further the processing on the result that it obtained through the call. Okay, so that's a typical example I just gave there with Bluetooth. Now, we've got what we call the dual mode of operation, which provides us with the means of protecting the operating system from errant users. It's very crucial that the operating system is protected from users in general, but specifically from errant users, because it is the core of governing body of the computer. So should it be tampered with, maybe a file deleted, that's why most of the files that are involved with the operating system are normally not visible. Is that okay? Should it be tampered, it can break, and if it breaks, the computer cannot operate. In order to accomplish this protection, it's done by designating some of the machine instructions that may cause harm as what we call privileged instructions. The hardware allows privileged instructions to be executed only in kernel mode. Yeah, so they're not accessible by the user at the end of the day. If an attempt is made to execute a privileged instruction in user mode, the hardware does not execute the instruction, meaning the CPU won't execute it, but will rather treat it as an illegal or a trap, and traps it to the operating system, meaning it will treat it as an exception, and it will throw an exception within the execution of the operating system. So the instruction to switch to kernel mode is an example of a privileged instruction. Some of other examples include input-output control, timer management, interrupt management, as well as interrupt management. Those are some of the what we call instructions that are privileged because they can only be executed in kernel mode. As we shall see throughout the text, there are many additional privileged instructions besides the actual fact of switching from the actual instruction of switch that consists of switching from user mode to kernel mode is actually one of those privileged instructions. Okay. All right. So the concept of modes can be extended beyond 2 modes, in which case we'll speak dual mode means kernel and user only. But if we extend it beyond 2 modes, we speak about multi-mode then. Okay. In that case, the CPU uses more than 1 bit, therefore, to set and test the mode. Let me ask a quick question. Let's say we've got 8 modes. Up to how many bit mode do we need? Anyone? Come on, this is basic digital systems. With 8 different modes in a multi-mode operating system, how many bit modes do we need to establish up to 8 modes? Stiba?
I'll just guess and say 8.
Pardon? Hello? The way you know that is that you work out with the number of bits that you need to represent the 8 modes. So when you speak about 8 modes, starting with mode 0, of course, it will end at mode 7. And mode 7 in binary is just 111, right? So you need up to 3 bits to establish an 8-bit mode, 8-bit multi-mode operating system. You agree? Are you there? Okay.
Yes, sir. I'm here.
Okay. Okay, so now the other thing is, in a special manner, a CPU might be supporting what we call virtual machine manager or virtualization, basically, meaning it's doing maybe processing for remote computers or computer systems. In that case, to distinguish between how do you call it? To distinguish between its local processing as well as its virtual processing task, it would have an extra bit for that. That bit will define whether we are in a virtualization mode or whether we are in local mode. So let me quickly explain this. So, and what that means is that thanks to the virtualization bit mode here, we can still maintain all modes in either local or virtual. So, for example, let's take the dual mode operating system, where we've got user mode and kernel mode. If on top of that, we are talking about maybe a server computer, which has got both virtualization and localized computing, it will have an extra bit. And if that bit is 0, for example, we are in local mode, that will mean if the virtualization bit is 0, and in addition to that, the extra bit is 0. So that will make the 2 bits be 0, 0. If the 2 bits are 0, 0, so both the virtualization bit mode as well as the actual bit mode the above zeros, then we will say that we are in local mode, in local kernel mode. But if you've got 0 and 1, that will mean we are in local mode under user mode. But if we've got 1 for the virtualization bit and 0 for the normal bit mode, then we'll say we are in remote or virtual machine kernel mode. The same way we can be in virtual machine user mode. This is exactly what's happening with the VirtualBox we installed. When we install it on Windows, we are basically able to switch between depending on whether we are working on the virtual machine or on the actual physical machine, we'll be able to what is changing in between there is actually that virtualization bit mode. Hang on. Okay. Do you get it, guys?
Yes,
The
sir.
same can happen when we've got a virtual bit mode. Even in a multi-mode scenario, we might still have an extra bit. Let's say 8-bit mode. We might have a 9th bit that actually tells us whether we are under virtual mode or under local machine processing mode. Okay, so yeah, that's the idea there. Okay, I just want to write it so that it makes much more sense. So you have your normal bit mode. Let's start with dual mode operating system. You've got a normal bit mode, then if this machine supports virtualization, you'll have a virtual bit mode as additional. Here we know 0 means kernel, 1 means user. But if you are running a virtual machine on the same computer, you might have 0, 0. When it's 0, when the virtual bit mode is 0, then you are in local kernel. Here you are in local kernel, meaning physical kernel, basically physical machine kernel. Local also means physical, so you are busy with the physical machine. This, if it changes to 1, you could be still in kernel or user, but for the virtual machine. So this will be virtual kernel or virtual user. Is that okay? Okay, I think that's clear now. I wanted to just insist on the, on the virtual machine manager, which is a portion of the operating system that manages all possible virtual machines that might be installed on that specific computer. So within the code of the operating system, you'll find a section or a class that we call the Virtual Machine Manager, VMM, which is in charge of managing any possible virtual machine that might be running on the specific computer on which this operating system is installed. Okay. Okay, so now I also want to speak about in the virtualization mode, we might have, the VMM has more than, has more privileges than the user processes, but fewer than the kernel. So it's more of an in-between type of mode. It needs that level of privilege so that it can create, manage virtual machines, changing the CPU state to do so. Sometimes two different modes are used by various kernel component. We should note that as an alternative to modes, the CPU designer may use other modes to differentiate operational privileges. Okay, so the differentiation between operational privileges is not only software, a software matter, it can also be a hardware matter. The CPU designer may therefore, as he designs the CPU, cater for that at hardware point of view. Typical example, with the Intel 64 family of CPUs, they do support what we call 4 levels of privileges. And they support virtualization, but does not have a separate mode for virtualization. So it may happen that you also have a CPU that supports virtualization, but this virtualization is set up not in software, but it's set up by hardware privileges. Okay. So now if we look at the life cycle of instruction execution in a computer system, meaning all the way from fetching instructions to retrieving and so on, we can now see that initial control at the end of the day resides in the operating system. The operating system is really what controls everything from the beginning at least. It is there that instructions are executed in kernel mode. When control is given to the user application, the mode is changed to user mode, as we discussed, and vice versa. Sometimes we can go back from user mode to kernel mode as well. Okay. What do we call system calls? System calls refers to actually instructions that are issued by the operating system for the CPU to execute. Okay. So, and system calls are intermediate calls or instructions generated by the operating system on request by a user application. Okay. So a system call is invoked in a variety of ways, depending on the functionality provided by the underlying processor. In all forms, it is the method used by a process to request action by the operating system. So I think that's the best definition then actually there of what a system call actually represents. So it is the method that is used by a process, meaning a user application, to request action by the operating system. A system call usually takes the form of a trap to a specific location in the interrupt vector. This trap can be executed by a generic trap instruction, although sometimes, although some systems, one of them being the MIPS, which stands for million of instructions per second, which is a special type of system or CPU. Some of these CPUs have a specific syscall instruction to invoke a system call. So in general, system calls are executed as traps to the operating system, but there exist some special cases of computer systems that execute system calls by means of a special instruction that is often named syscall. Very important. It's very important to know this, the trap, the system call as keywords, because we use that as we do programming in C and apply concepts of operating system. So when a system call is executed, it's typically treated by the hardware as a software interrupt. Control passes through the interrupt vector to a service routine in the operating system, and the mode bit is also changed accordingly. Normally it will switch from user to kernel, because a system call is an instruction at the end of the day of the operating system. Although it originates all the way from the user, the fact that it goes through the operating system, when it's issued to the CPU, it comes in kernel mode. So the system call service routine, which handles system calls, is part of the operating system. So as part of the operating system design, one must write a piece of code that is handling all the system calls. The kernel examines the interrupting instruction to determine what system call has occurred. A parameter indicates what type of service the user program is requesting. Additional information needed for the request may be passed in registers as the user instruction is issued to the operating system. It doesn't just come as a command, it comes as a command and sometimes accompanied with parameters that are sent to registers within the CPU. So that when the CPU is about to execute that specific system call, it can also read from those parameters from those registers to draw the parameters that are needed in the execution. Okay. The kernel verifies that the parameters are correct. So part of the role of the kernel here as a system call is issued is also to do validation of parameters from the registers, is read from the register, and then execute the request and returns control to the instruction following the system call. So the system call is interjected in between different instructions that the CPU was busy with. Hence we say it comes in the form of a trap, or in certain cases in the form of a syscall instruction. But the point is it interrupts the execution of a program. And that's why once it's done being handled by the system call service routine, the program should actually be able to return to the next instruction after the instruction it had stopped at before the system call was issued. Of course, to keep track of which instruction we last executed, computer systems make use of a hardware memory storage that we call the stack. Okay, that is very critical to know. Okay, it's also the kernel that verifies the parameters validity, besides the execution of the instruction at the end of the day, in its role of supervisory program, of course. Now, whenever there's no hardware supported dual mode, meaning the hardware doesn't support user mode as well as kernel mode, this can be a serious shortcoming in an operating system. Because the operating system as a software may be good in terms of catering for a dual mode, but if hardware that is running on does not allow for that dual mode, then it's almost pointless. And that's the example of MS-DOS, written for Intel 8088, which is a very old operating system, MS-DOS. That's the origin of Windows, which has no mode bit, and therefore cannot choose between kernel mode and user mode. And this justifies why on Windows sometimes when you want to do certain things that you are not able to do on the GUI, you tend to refer back to the command line whereby you actually run MS-DOS. And with the command line, you can actually view. You can view. You've got extra privileges because you can view some kernel dedicated files. Okay, because you've got access to kernel dedicated calls or instructions. So a user program running can wipe out the operating system by writing over it with data. That's what justifies the fact that we protect certain type of instructions and files to be only executable in kernel mode. And that's why, just to link this to security, that is why most hackers often go the MS-DOS route. Hackers, all these malicious softwares, they often execute in not on a GUI. Very few hackers will take a mouse and start doing things with your computer. Most of them will launch the command prompt and then execute those commands to alter your computer. For example, to encrypt all your file and then ask for a ransom, which we call ransomware, and many other attacks you may think of, man in the middle attack, etc. Okay, most of the times you know you've been attacked when you suddenly see your command prompt window popping without you having opened it. Okay, all right, so that was very important. So once hardware protection is in place, it detects errors that violate modes. These errors are normally handled by the operating system by means of a dialog box in Windows, for example. If a user program fails in some way, such as by making an attempt either to execute an illegal instruction or to access memory that is not in the user's address space. Then the hardware traps to the operating system. The trap transfers control through the interrupt vector to the operating system. So the operating system takes over. The trap transfers control through the interrupt vector to the operating system just as an interrupt does. So it's very similar to an interrupt because this is not previsible. When it's just that when it happens, then it must be signaled to the CPU for it to stop the execution of certain processes, the ongoing processes, and first handle it through the operating system before resuming. So this situation is handled by the same code as a user requested abnormal termination. An appropriate error message is given, and the memory of the program may be dumped, just to free the memory. The memory dump is usually written to a file so that the user or programmer can examine it and perhaps correct it and restart the program. So that specific file to which the errors are written is what we call the log file. I'm sure you've encountered a log file in the past. You see this even with microcontrollers. When you have an error in your simulation, let's say in Proteus, because I'm assuming you guys use Proteus, if there's an error, it will pop up a log file where it will write the source of the error as per the simulation, which is a software, guidelines and principles that were just happen to be violated. Maybe there's no ground point, or maybe you have contention between your positive and negative within your simulation, etc. The next concept when it comes to operating system operations is timer, because without time, a computer cannot function. A lot of features of a computer will not be accessible. So timer is part and parcel of the operating system operations. It's actually one of the key one of the key operations of the operating system. We must ensure that the operating system maintains control over the CPU. We cannot allow a user program to get stuck in an infinite loop. How does the operating system handle the fact that we don't allow a program to be stuck in an open loop? Anyone who has an idea there? How would the operating system handle that? How would the operating system ensure that we are never stuck in an infinite loop as it executes? Maluleke?
Wouldn't it force it to close or stop?
But how is the timer involved? Stiba? Think.
So when an interrupt occurs,
Pardon?
once an interrupt occurs,
I can hear you hardly. The answer is simple. When you start the execution of every program, in parallel, a timer is also started. This timer has got a timeout value, which is an estimate of how long it would take for that program to execute successfully. Should the program take longer than that, we know that something wrong happened. And what do? We terminate the program. So you understand how a timer would help in making sure that the program is never stuck. It's by means of a timeout timer. Pardon?
I'm saying we get it, sir.
Okay. Yeah. A timer can be set to interrupt the computer after a specific period, exactly what I just explained. A variable timer is generally implemented at a fixed rate clock and a counter. And I've explained this concept of timer. When it comes to timing within any computer system, it's guided by a clock. Remember, a clock is the reference signal when it comes to timing in any computer system. So the clock is at fixed rate because if it's a 12 megahertz crystal, it's a 12 megahertz crystal. If it's a 1.6 gigahertz crystal, then it's a 1.6 gigahertz crystal, and so on. But we do make out of a fixed rate clock, we can generate sub clocks at different rates. That's why we end up with a variable rate. And that's how we run different timers. And you know this very well from digital systems. And of course, you know that to achieve clock division, you make use of flip-flops. You remember. And if you look, for example, in the microcontroller's memory organization, architecture, when you look at the clock path, there's always a clock division module, which tells you get half of the original clock here, you get 1/4 of the original clock, 1/10 of the original clock, and that's sometimes configurable. And it also involves what we call the phase locked loop, a PLL, which ensures that once you've changed from the original clock to a new clock, we lock it there so that it doesn't change back to the original clock. So from a fixed rate clock, which is what we call, it could be a crystal, it could be that small signal generator that we use at the beginning to generate the original clock. We can actually generate a variable rate other clocks, okay, by doing frequency division, of course. Meaning the constraint is that no other clock running in a computer system can be faster than the mother clock, which will be the crystal in that case. So if a microcontroller is interfaced with a 12 megahertz crystal, pardon? If a microcontroller is interfaced with a 12 megahertz crystal, you can get sub clocks of that, meaning 6 megahertz, 4 megahertz, 3 megahertz, but you can't have higher. Okay. All right. So that was important to understand how timers intervene in an operating system and how they are very useful to ensure a proper operation of an operating system. So now, when it comes to process management, a program does nothing unless its instructions are executed by CPU. Yes, because when we say a program here, we're talking about the user application. There wouldn't be any result of a user application if its specific instructions haven't been passed onto the CPU by the operating system and the CPU hasn't actually executed them. A program in execution is what we call a process. A time-shared user program, such as a compiler, will be seen as a process. A word processing program, such as Word, Word, Notepad, etc., that is being run by an individual user on a PC is also a process from the moment it's running. A system task, such as sending out to a printer, that's a system task, can also be a process. So processes can be both user instructions or even system instructions. For now, you can consider a process to be a job or a time-shared program. But later, you learn that the concept is more general, and that is in chapter 3. More general, it is possible to provide system calls that allow processes to create sub-processes to execute concurrently. So for now, we keep it as a job, but we'll generalize it to system calls as well in chapter 3. So a process needs certain resources, of course. So it's a program under execution, and for it to execute, it needs a certain number of resources. It needs some CPU time, it needs some memory, it needs access to files, and sometimes it even involves input-output devices, such as a mouse, a barcode scanner, a keyboard, etc. These resources are either given to the process when it's created or allocated to it while it's running. By the way, and we'll learn a bit more about that when we study processes in chapter 3, a process is basically a temporary concept in a sense that it gets birthed, it runs, then it dies. It dies when it's done executing the task that were allocated to it. But it also needs resources, and the allocation of resources to a process, because there is not just one process that's running on a computer. At the time, there are normally many. So the allocation of these resources, because these processes are all competing for these resources, memory, IOs, etc. The allocation of resources is normally managed. The allocation of resources to processes is normally also managed by the operating system. Okay, so now the resources are either given to the process when it's created or allocated to it while it's running. In addition to the various physical and logical resources that a process obtains when it is created, there are some various initialization or data input that may be passed along. For example, consider a process whose function is to display the status of a life on the screen of a terminal. The process will be given the name of the file as input, so that's one of the data that it needs, and it will execute the appropriate. So the process, is displaying the name of the file on the screen, but it must get that name of the file from somewhere. Hence, the name of the file is passed to it as an input. Then it executes the appropriate instructions and system calls, both instructions and system calls, in order to obtain and display the desired information on the terminal. When the process terminates, the operating system will reclaim any reusable resources, meaning out of the resources that the process was occupying when executing, when it dies, the operating system takes back those resources in order to reallocate them to other processes. We emphasize that the program by itself is not a process. It has to be a program that is executing or that is running to become a process. So a program as a concept is a passive entity, like the content of a file stored on a disk, for example. But a process is an active entity, meaning it's something that involves movement, meaning it's a program being executed, which means it has got steps that get followed and one after the other and so on in a specified manner. So we speak about a single threaded process to be the one that has one program counter, specifying the next instruction to execute. We'll study more about threads in chapter 4 because processes and threads are sometimes used interchangeably, but there is a nuance in the sense that they are different. As you can see already, a process is a program under execution, but when it comes to a thread, a thread could be a piece of a program being executed, and that could be executed concurrently with another piece of the same program. But in a process, it's one piece of a program at a time. Two cannot be executed at the same time. But in a threaded system, pieces of the same program can be executed at the same time as long as there's more than one program counter that keeps track of where we are in the execution. So the execution of a process is normally sequential, especially, and it's exactly, so a process is actually a single thread, a single threaded operation as well, to put it in general. So to define a process by means of a thread, we say that a process is a single threaded operation, meaning the type of operations at the operating system that execute one sub-process at a time. There's no concurrency of any kind. Okay, so the CPU executes one instruction of the process after another until the process completes. Further, at any time, one instruction at most is executed on behalf of the process. At most, because there may be times where the CPU is not executing anything, which will mean that 0 instructions are being executed. And this is because, as we mentioned earlier on, the operating system is an event-driven or interrupt-based program. They are nevertheless considered two separate execution sequences. So even if two processes may be associated with the same program, they are considered to be separate. They are executed one after the other at the end of the day. A multi-threaded process, on the other hand, and I'll conclude there, is the type that has got multiple program counters, each pointing to the next instruction to execute for a given thread. So a given thread has got a lot of instructions that can be maybe subdivided into 2, into 3, into 4, and they can all execute at the same time. And because we have multiple program counters, we can keep track of where we are in each portion, and when it's necessary to get results from one thread into the other because it needs it, and so on. That way we do a bit of parallel processing, but this time on a single core, and ensure that we improve on efficiency. But of course, multi-threading requires a proper study of interdependability between the processes so that you can know which ones to execute and when. Which instruction to execute and when, because even if you're executing them more or less in parallel, you still have to know which one feeds its output as input to the other, because so that once it's done executing the other one can wait for it to finish in order to get something from it and move on. And how you arrange your different instructions at an operating system point of view plays a big role in the type of performance you get in the end. I'll conclude there for today. I'll see you guys.